Good morning to all participants. Okay, start the meeting. Uh, Good morning to all participants. Uh, Myself is M. Praveen, Assistant Professor, EC Department, Savitha Engineering College. I welcome you all for the online STTP on Bloom's Taxonomy, Higher Order Thinking Skills in Electronics and Communication Engineering. Today is day 5 of module 5. So, starting from module 5 on day 1, Puspada ma'am had discussed about some of the gate questions from electronic circuits. On day 2, Dr. S. Nagarajan sir had a discussion with some of the gate questions from 2010 to 2019 gate questions from LIC. On day 3, again, Puspada ma'am discussed the remaining gate questions from electronic circuits. On yesterday, Ms. Kalapriya ma'am had discussion with the gate questions from 1996, gate questions from 1996 to 2010. On today, we have the remaining gate questions, that is from gate questions from 1987 to 1995. So that's the remaining gate questions from linear integrated circuits. So we are going to discuss the remaining questions from on today's session. Okay. So before start our session, let's see what is the syllabus for the linear integrated circuits. So actually, linear integrated circuits is the subdivisions of the analog circuits. So in analog circuit sections, we have the syllabus from electronic circuits and linear integrated circuits. So today we are going to discuss about LIC. So we'll see what about the syllabus for the LIC. So starting with LIC, the first one is about the OPAM, that is operational amplifier circuits. That is the internal circuit diagram and the ideal characteristics, AC, DC characteristics. So that is the first topic. And the active filters is nothing but the types of filter which comes under the integrator, differentiator, band pass filter, low pass, high pass, band rejection filter. So these are the topics which will be comes under the active filters. Then the next one is sinusoidal oscillator, which is nothing but the RC phase shift oscillator and Wien-Bridge oscillator. Then the criteria for oscillation. So we have to condition. So the criteria for oscillation. Then the next one is a single transistor and op-amp configuration. So then the next one is function generator. So we got the IC for the function generator. That topic is also very important. Then the next one is wave shaping circuits. Wave shaping circuit means that is the we have the applications of op-amp. That is a Smith trigger and that are the topics from the wave shaping circuits. And 555 timer. So by using 555 timer, we can use we can design the monostable and stable multivibrator. Then the next one is voltage reference circuits, which is called as a voltage regulator. Then power supply is nothing but the regulated power supply, then ripple removal and regulation. So almost all the topics are very important for the LIC. So if you take enhanced syllabus starting from unit 1 to unit 5, so all the 5 units are very important. So and if you take a gate question paper and from LIC, at least you'll have 3 questions from LIC and 3 questions from the electronic circuits. Okay. So now move on to the first question. So this is the first question, which is asked in GATE 1987. So in figure, if the CMRR, common mode rejection ratio of the op-amp is 60 dB, then the magnitude of the output voltage is dash. Okay, so here a circuit is given. So and a CMRR value is given, which is 60 dB, which is given as in decibel. Okay, so then what is the output V naught? So we have to find what is the output voltage V naught for the given circuit. So four options are there. So option A is 10 millivolt, option B is 100 millivolt, option C is 1 millivolt, and option D is given as 40 millivolt. Okay, so to find output voltage, first what we have to do is, first we have to divide the whole circuit into two sections. Okay, so here this part will be the first section, and this one is going to be the second section. So if you take first section, we have the balanced bridge circuit. Okay, we have R. So this is called as a balanced bridge circuit. And if you take a second part is nothing but a differential amplifier. So we have the input from both inverting as well as non-inverting. Here it is minus, here it is plus. So we have the input from both inverting as well as non-inverting terminal. Therefore, the second section is nothing but a differential amplifier, and first section is called as a bridge circuit. Okay, so first we have to find what is the output of the section 1. So here for the first section 1, we have to output terminal. Let it, this one is considered V naught of 1, and this one is considered V1 and V2. Let it be V1 and V2. So V1, V2 are the output of the first section. So once we find V1 and V2, then we can easily find what is the output for the V naught. Okay, let's see. So let this two nodal point be V1 and V2. So if you take a balanced circuit, here all the resistance are equal, R, which means that the circuit is in balance condition. So if you take all the four resistance, all the four resistance are having equal or value, and the input to the balance bridge circuit is 2 volt. So now we have to find what is V1 here and V2. So V1 is very simple. So this is called as V1. Okay. So to find V1, we have to consider these two resistance and this 2 volt. Okay. So by applying voltage divider formula, so simply are going to apply voltage divider formula here. So here we have R, here we have R, and the voltage applied to here is input voltage is 2 volt. So now if we applied a voltage divider, then V1 is equal to the opposite resistance is R divided by the summation of two resistances R plus R 2R. Therefore, R divided by 2R into the input voltage is 2 volt. So now 2 will get cancelled, R will get cancelled. Therefore, V1 is going to be 1 volt. Actually, I have not mentioned the steps here. Simply, I have written V1, V2 as 1 volt. Okay. So how it is getting us 1 volt is just by applying a voltage divider formula. So R divided by R plus R. So that is R divided by 2R into 2 volt. Okay. So 2 cancel, R cancel. Therefore, V1 is equal to 2 volt. Similarly, for V2 also, we are having the same 1 volt, same thing. We are having two resistance, and this is a V2 node. So V2 is nothing but R divided by 2R into 2 volt. Therefore, RR cancel, 2 cancel. Therefore, V2 is also going to be the 1 volt. Okay. So now, now we got the output for the first section of V1, V2. Now this V1, V2 are the input to the second part. Second part is nothing but the differential amplifier. So if you know the circuit diagram differential amplifier, then you can able to easily understand the concept. So here we have 1 kilo ohm, 1 kilo ohm. This is called as R1. If you take a differential amplifier, this is called as the R1 resistance, and this 100K is called as the R3. This one is R1 and this is R3. This is a feedback resistance. Okay. So and the formula, we all know the formula for the difference amplifier. So V naught is nothing but the difference of two inputs. So here V1, V2 are the two inputs which are applied to the differential amplifier. So the general formula for the difference amplifier is V naught is equal to the difference of the input voltage into R3 by R1. So here R3 is 100K. So this is R3 and this is R1. This is a feedback resistance. Okay. So the general formula for the difference amplifier is V naught is equal to difference of voltage into R3 divided by R1. So we can write V2 minus V1. This is a difference voltage as VD. We can mention V2 minus V1 as VD, and R3 by R1 is nothing but it is a differential gain. Okay, so that is A suffix D. So we can write the same formula as V naught is equal to VD into AD. Okay, so now we can easily find AD. So AD is nothing but R3 by R1. So R3 value is given, which is 1K, and R1 value is 100K. So if you divide 100K by 1K, you'll be getting the value of the differential mode gain as 100. So here, actually, here the circuit is which is not mentioned here. Therefore we have two cases. Okay, suppose if you take most of the question, they will simply given that op-amp is ideal, so op-amp is non-ideal, that will be given, but here it is not mentioned. So therefore we have two scenario. First, if CMRR is infinite, so if the op-amp is ideal means, then the common mode rejection ratio is going to be infinite. So if CMRR is infinite means, we know the formula for CMRR, it's nothing but AD by AC. Okay, if CMR is infinite means, then what will happen? AC is 0. So AC means common mode signal is 0. Generally, if you take a ideal op-amp, if you take a ideal differential amplifier, the common mode gain is going to be 0. So if it is 0 means, then only the CMR is going to be infinite. But here it is not mentioned here. Therefore, we have to consider the two scenario. So if CMR is non-infinite, if it is not infinite means, then we know that formula for that V naught is nothing but, so if CMR is infinite means, we have the formula is V naught is equal to VD into AD. So if CMR is if it is not infinite means, then we have to consider the common mode also. Okay, differential amplifier can be operated in two mode. One is a common mode and differential mode. So if CMR is infinite means, then the common mode is suppressed. If CMR is not infinite means, then we have to consider both the differential mode as well as the common mode. So therefore the overall output V naught is going to be here is ADVD, which is a differential mode gain into differential voltage, plus AC into VC, where VC is nothing but V1 plus V2 by 2. Okay, so if you know the differential amplifier, then you can be able to then if you are know the topics of differential amplifier, then the formula is well known for all the others. So V naught is equal to ADVD plus ACVC. Okay, so now CMR value is given, which is 60 in dB. Now we have to find what is CMRR. Okay, so simply you have to take 20 log of CMRR in dB. So 20 log of 60, you'll be getting the values nearly equal to 1000. Okay, so now we already found AD value as 100. So AD value we already found as 100. So now we have to find what is AC. So AC is equal to AD by CMRR. So AD value is 100 and CMRR value is 1000. So now we got AC value as 0.1. Okay. So now we got 0.1 of AC. So now we know AC value, AD value, CMRR value, and remaining thing we have to find is VD and VC. So VD is nothing but difference of V1 minus V2. Here both are 111. Therefore VD is going to be 0 volt. Okay. Next VC is nothing but V1 plus V2 by 2. So V1 value is 1 and V2 value is 1. Therefore 1 plus 1 divided by 2, which is equal to 1 volt. So now we got all the values. So just simply we are going to substitute all the values in V naught. It's equal to AD VD plus AC VC. Here already VD value is 0. Therefore this part is going to be 0. And for common mode gain, AC value is 0.1 and VC value is 1. Therefore 0.1 into 1, which is equal to 0.1 volt. So but actually the answer here is in terms of millivolt. Therefore, so we have to convert this 0.1 volt into millivolt. Therefore, we will be getting V naught is equal to 100 millivolt. Okay. So therefore, answer for the question is option B, which is 100 millivolt. Next, move on to the second question. This is a question which asked in GATE 1987. Okay, the op-amp shown in figure below is ideal. So here, if you see the questions here it is mentioned as the op-amp is ideal. Okay, so if the op-amp is ideal means, then what about the op-amp characteristics is? So here the difference of voltage. So if the op-amp is ideal means, the difference of voltage between the inverting non-inverting is 0, and second characteristic is input impedance is infinite, and the current flow through the inverting non-inverting is 0. So these are the ideal characteristics of an op-amp. And so here it is clearly specified that op-amp is ideal. Then here they have given R value as root of L by C. Okay, R value is going to root of L by C. The phase angle between V naught and VI. So we have to find what is the phase angle between V naught and VI. So V naught is the output voltage, VA is the input voltage. So we have to find what is the phase angle for V naught by VI. So here omega value is given, which is 1 divided by root of LC. So 4 options are given. So pi by 2, pi, 3 pi by 2, and 2 pi. Okay. So so what we have to do is first we have to find V naught divided by VI. Okay. So V naught divided by VI. Before to find V naught by VI, first we have to see what is for the given circuits. Okay. Actually, the given circuit is nothing but it is a inverting op-amp. Okay. So here non-inverting terminal is grounded. So we have the input only at the inverting terminal. Therefore, the given circuit is nothing but inverting op-amp. So therefore, we know the formula for the inverting op-amp, which is nothing but V naught divided by VA, which is equal to minus RF divided by R1. So here feedback resistance is nothing but the combinations of inductance and resistance, and here the input resistance is nothing but the combinations of resistance and capacitance. Okay. So now V naught divided by VA is nothing but minus RF divided by R1. So RF is nothing but Z2 and R1 is nothing but Z1. So minus Z2 by Z1, which is equal to, so if you take feedback impedance, here we have inductance and resistance. If you write these two components in S domain, you will be getting SL plus R. Okay, SL plus R divided by, if you take this one, here we have the capacitance and resistance, therefore R plus 1 by SC. Okay, R plus 1 by SC. Now we have to simplify the numerator denominator. So our denominator we are having SC. Therefore, cross multiply, if you do cross multiply, you will be getting 1 plus SCR divided by SC. And this SC will be moved to the numerator. Now the simplified equation is minus SCR plus S square CL divided by 1 plus SCR. Okay. So now we have to replace S value by J omega. So then V naught by VA is equal to minus of J omega RC minus omega square LC divided by 1 plus instead of J, you have J omega RC. Okay. So after replacing all S by J omega, then we have to substitute R as root of L by C, which is given the question itself. So we have to replace R by root of L by C, and omega is replaced by 1 by root of LC. So first we will replace R by root of L by C. So if you replace, here we have R, here also we have R, just we have to replace this 2R by root of L by C. So after substituting here, now after substituting the R value here, the terms will be cancelled. Therefore, you will be getting the simplified equation as minus of J omega root of LC minus omega square LC divided by 1 plus J omega into root of LC. So now we have to replace omega by 1 by root of LC. Okay, so now we have to replace omega by 1 by root of LC. So here instead of omega, we have to replace root of LC. Here also root of LC. Therefore, these two terms cancel. Here also LC cancel. So here also root of LC cancel. Therefore, finally, if you simplify, you will be getting V naught by VA is equal to 1 minus J divided by 1 plus J. So this is a final reduced equation of V naught divided by VA. So now what we have to find is we have to find the phase angle of V naught divided by VA. So now what we have to do is we have to take phase angle for V naught divided by VA, which is nothing but we know the formula, that is tan inverse of Y by X. So if you take numerator, this is a Y term, this is a X term. So Y divided by X. Similarly for denominator, this is Y term, this is X term. So the formula is tan inverse of Y by X. So if you use a formula for numerator, you will be getting tan inverse of Y. Here it is minus 1. So minus 1 by 1 minus. So we have the denominator term, therefore minus of 1 plus J. So here Y is J and X is 1. Therefore tan inverse of 1 by 1. So finally we are getting tan inverse of minus 1 minus tan inverse of 1. So we know that tan inverse of minus 1 is nothing but minus pi by 4, and similarly for tan inverse of 1 it is pi by 4, and here we have minus, therefore minus pi by 4. So if you subtract these two values, we will be getting minus pi by 2. Actually the answer is minus pi by 2, but if you take a question, minus pi by 2 is not given, therefore we have to convert to any one of the answer here. So we can write minus pi by 2 in terms of 360 minus 90. So 360 minus 90 is nothing but minus 90. So the quotient will not be changed here. Therefore, we can write as 360, that is 2 pi minus pi by 2, which is same as minus pi by 2. Okay. So now if we cross multiply, we'll be getting 4 pi minus pi by 2, which is nothing but 3 pi by 2. Okay. Therefore, the answer is option C. Okay. So actually we got as answer is minus pi by 2, but minus pi by 2 is not given in the answer. Therefore, we have to convert to any one of the four options. So we know that 360 minus 90 is nothing but minus 90. Therefore, we can write as 2 pi minus pi by 2. So now for 2 pi minus pi by 2, we can cross multiply. We'll be getting 4 pi minus pi, that is 3 pi by 2. Okay. So answer is option C. The third question, the op-amp of a figure has very poor open loop voltage gain of 45, but is otherwise ideal. The gain of the amplifier equals dash. Can you guess what is the answer? So four options are given. A is 5, B is 20, C is 4, and D is 4.5. Can you guess what is the answer? First, see what is the given circuit, whether it is a inverting mode or non-inverting mode or differential mode. So please check. After that, after getting this, after that you have to use a formula for the circuits and tell me what is the answer. Can you guess what is the answer for the question? Many of you are straight away they are writing the answer as that is here it is in here it is here. If you take the circuit, so here we have the input to the non-inverting mode. So simply everyone will write the formula as V naught divided by V in is equal to 1 plus RF divided by R1, but actually the answer is wrong. So if you write 1 plus RF divided by R1, you will be getting the answer as 5. So 5 is actually wrong answer. So answer 5 is also given here, but 5 is wrong. So why it is wrong is, just see the questions here. The op-amp of a figure has a very poor open loop voltage gain of 45, but is otherwise ideal. So here it is clearly mentioned that it is not an ideal op-amp. So therefore, we cannot use the formula of V naught divided by VA is equal to 1 plus RF divided by R1. So if you use that formula, you'll be getting 5, but 5 is not a correct answer. So clearly the question itself they given, the op-amp is not a ideal op-amp. So if only if it is ideal op-amp, we can use V naught divided by VI, which is equal to 1 plus RF divided by R1. Okay. So now, if you use that formula, you'll be getting 5, but this is wrong answer. So now, what we have to do is, here we have a nodal point. So this nodal point voltage is V minus. Why it is V minus? Is it is a inverting terminal, therefore V minus, and here V plus is V in. So the difference of, so the difference we can write. So now we can write output V naught. So output V naught is nothing but the difference of V plus and V in minus into open loop gain. That is general formula. So therefore V naught is equal to open loop gain, that is AOL into V plus minus V minus. Okay. So now open loop gain is given, which is 45. So 45 into, now we have to find what is V minus. So V plus is V in, and for V minus we have to apply voltage divider formula. So V minus is nothing but the opposite resistance is 2. So 2 divided by 2 plus 8 into the V out. Okay. So if you simplify, you'll be getting V naught is equal to 45 instead of V plus, we can write as V in. Okay. So V in minus 90 V naught. So now V naught and V naught, so will be become 10 V naught, which is equal to 45 VI. So now we can write V naught divided by VA, which is equal to 45 divided by 10, which is 4.5. Okay. So the answer for the question is 4.5. Okay. Let's move on to the next question. In order that the circuit of figure work properly as a differentiator, it should be modified to dash. I think it's a very simple question. So here the circuit diagram is given. So we have to modify the circuit so that it can be operate as a differentiator. Can you guess what is the given circuit? So here the circuit diagram is given. Can you guess what is the circuit diagram? Anyone? What is the circuit diagram here? So circuit diagram which is shown in the figure is nothing but it's an integrator. Okay, so integrator will have R and we have the feedback capacitance. Okay, so now what we have to do is we have to convert the circuit into the differentiator. Okay, so to convert the circuit into differentiator, what are the modifications we have to do? That is the question. So if you take, this is a practical differentiator. So if you know the concept differentiator, then you can be able to remember this. So this is a practical differentiator. So if we take a practical differentiator, we have the resistance and capacitance which is in series with the inverting terminal. And if you take a feedback, you have the feedback resistance along with the capacitance which is parallel to the feedback resistance. This is the actual practical differentiator. But here, this circuit diagram given, which is nothing but an integrated circuit. So we have to modify the circuit, okay, so that it will be working as a differentiator. So what we have to do is, here if we compare these two, here we have resistance, so here also we have resistance. So what we have to do is we have to simply add one series capacitance to the resistance, okay. And similarly, if you compare feedback, so feedback part, just compare the feedback part. Here we have the capacitance, so here also we have the capacitance, and the only thing which is not mentioned here is the feedback resistance. Therefore we have to add a parallel feedback resistance here. So this is a modification we have to do. Therefore answer for the question is connecting a capacitance in series with the resistance and one feedback resistance in parallel with the capacitance. So then it will automatically be working as a differentiator. That is a practical differentiator. Okay, let's move to the next question. In figure, the op-amp is ideal and its output can swing between -15 and +15. The input voltage VA, so this is VI. Okay, so VA, which is 0 for t less than 0, is switched to 5 volt at the instant t is equal to 0. Given that the output voltage V0 is plus 15 volts for t less than 0, sketch on the same diagram the waveform for V0 and VI. You must give the values of important parameter of the sketch. Okay, so actually they have given a circuit diagram and they have given the condition for the input and the output. And what we have to do, what we have to find is we have to find what is the graphical waveform for input and output V0 and VA. Okay. So I think it's a very simple question. So if you take a circuit here, so the circuit is nothing but it's an integrator. Okay, so we have the resistance at input and we have the feedback capacitance. Therefore, the circuit is nothing but it is a integrated circuit. So so we have to find what is V naught. So if you know the derivations of integrator, then you can directly apply. So if you does not know the integration formula, then we have to apply the nodal voltage here. Okay, so first we have to find for t less than 0. So for t less than 0, they have given the output voltage V0 is 15 volt. So question itself they have given. So V0 is 15 volts for t less than 0. And now let us assume the current flow through the resistance is IR. Similarly, here we have the feedback part. So here the current flow direction is from this way. This is opposite to IR. So therefore we can write IR is equal to minus IC. Okay. So here we have the inverting terminal. Therefore the current flow through the resistance is equal to the minus of the current flow through the capacitor. Therefore IR is equal to minus IC. So we can write IR as, so here IR, we can write IR as VI minus. So what is the voltage here? So here question itself they have given that op-amp amplifier is ideal. Ideal means the voltage at this node and this node is going to be same here. But here the non-inverting terminal is grounded. Okay. So here non-inverting terminal is grounded, which means that the voltage at here is going to be 0. If it is 0 means here also it is going to be 0. Therefore, we can write IR is nothing but VI minus V1. But here V1 is 0. Therefore, IR is equal to V1 divided by 1K. Okay. So V1 divided by R. So R, which is equal to, what about the formula for current flow through the capacitor, which is nothing but C into d by dt of the difference of voltage. Here the difference of voltage is, here it is 0. So here it is V naught. Therefore 0 minus V naught. Okay, so 0 minus V naught. So now if you simplify, we will be getting VA of t divided by we can take C here. Therefore VA of t divided by RC, which is equal to minus of, so here 0 minus V naught becomes minus V naught. Okay, so minus dV naught divided by dt. So now we want V naught, output voltage. So V naught is nothing but we have to take integration. If you take integration, then the differentiation will be cancelled. Therefore V naught will be getting as minus 1 by RC integration of 0 to t VA of t and dt. So if you know the formula, you can straight away write the answer here. If it does not know the formula, if you not know the formula, then we have to apply what is nodal voltage. We have to apply the nodal voltage. Then from nodal voltage we can find V naught. Okay, that's the second method. So now we got V naught. So first we are going to use the condition for t greater than 0. So what will happen for t greater than 0? So for t greater than 0, V naught of t. So we have the formula V naught of t is nothing but minus 1 by RC into. So what will happen for t greater than 0? So the input voltage, which is 0 for t less than 0. So if you take t value less than 0, the VA value is 0. If you take t greater than 0, then what will happen? It will be switches to 5 volts. So therefore, for t greater than 0, the input voltage VA of t is going to be 5 here. Therefore, we can substitute 5 here. So 5 into dt. So now if we write V naught of t, which is equal to minus 1 by RC, then integrate this VA of t, we'll be getting 5 of t minus V of 0 minus. So V of 0 is nothing but the initial condition. Okay, the initial condition of the output is 15 volt. Question itself they given. Initially the output is 15 volt for t less than 0. Therefore the initial condition value of the output voltage is going to be plus 15. Therefore V naught of t is equal to minus 5t. So into we have to substitute R and C value. So R value is 1k, C value is 1 microfarad. So if substitute R, C value here, you will be getting the final equation as minus 5t into 10 power 3 plus 15. So plus 15 is nothing but the initial condition of the output voltage. So initially it is plus 15. So now we are considering only for t greater than 0. For t less than 0, the output V naught is 15. Therefore, the initial condition is going to be plus 15 here. Okay. So now we have to substitute the t value here. So if we substitute t value here, we can get the graphical waveform. Okay. For t is equal to 1 millisecond. So this is the equation. For this equation, we have to substitute for various values of t. So if you take t is equal to 1 millisecond, you will be getting V naught of t value as 10. If you take t value as 2 millisecond, it is 5. And for 3 millisecond, it is 0. And 4 millisecond is minus 5. And for 5 millisecond, you will be getting the V naught of t as minus 10. So just you are going to substitute the value here for various value of t. And after getting all the values of t, then we have to plot the graph. So here in x-axis, we have the time period. In y-axis, we have to plot output voltage as well as input voltage. So for input voltage, we can directly write the waveform because it is given as the input voltage is 0 for t less than 0. So the input voltage VA is 0 for t less than 0, and after t, after beyond the value of 0, the value of VA is going to be plus 5 volts. So if you draw the diagram here, so for t less than 0, it is 0, and after t is equal to 0, you'll be getting the VA value as plus 5 volt. And similarly, if you take for output voltage also it is plus 15 volts for t less than 0. Okay, so only for t less than 0 the condition is given, and we have to draw what is for t greater than 0. Okay, so for t greater than 0, we have to plot the graph here. So if you plot for V naught, for t less than 0, it is plus 15 volt. And for t greater than 0, we have already found the various value here. For 1 millisecond, it is 10. So it is 1 millisecond. For 1 millisecond, we'll be getting the value as 10. And for 2 millisecond, it is 5. So let it be 2 millisecond, it is 5. And for 3 millisecond, it is 0. And for 4 millisecond, it is minus 5. And for 5 millisecond, it is minus 10. So this is the graphical waveform for output voltage and input voltage. Okay. Actually, it is a 5-mark question. Okay, so Let's move on to the next question. An op-amp has an offset voltage of 1 millivolt and is ideal in all other respects. If this op-amp is used in the circuit shown in the given figure, the output voltage will be dash. Four options are given: 1 millivolt, 1 volt, plus or minus 1 volt, and 0 volt. Okay. So we have to consider the offset voltage. So here offset voltage is given as 1 millivolt. So if this given offset voltage mean, then we have to the op amp is it's not a ideal op amp. Okay. So if we consider ideal op amp, here the difference of voltage between inverting non-inverting is zero. So here offset voltage is the voltage which is used to make the difference of value to zero. Therefore, the condition given is it is not an ideal op amp. Okay. So now, if it is a non-ideal op amp, then what we have to do is we have the formula. V naught is nothing but open loop gain into the difference of voltage, that is V plus and V minus. So this is a V plus and V minus. So V plus is 0 and V minus also going to be 0, but due to the certain parameter, the difference of voltage will not be 0. Okay. So in order to make the value to 0, we are going to apply an offset voltage. By applying offset voltage, we can make the difference of voltage to 0. So here the offset voltage is given, which is 1 millivolt. Okay. So now we can write V naught equal to AOL into V plus minus V minus. Now the V plus minus V minus is nothing but the offset voltage. Okay. So now what we have to do is we have to apply the nodal voltage here, V minus. So we have to find what is V minus. So V minus nothing but V naught into opposite distance is 1K, or we can write R1 RF. So V naught is V minus is nothing but R1, which is the opposite distance, R1 divided by the summation of two resistance R1 plus RF into V naught. So we can write the same equation as V naught is equal to 1 plus RF divided by R1 into V minus. Just we are keeping V naught here and we are moving the terms to the V this side. So now we are getting V naught is equal to 1 plus RF divided by R1 into V minus. So now V minus is nothing but the offset voltage. Actually here it is 0, V plus is 0, but here due to, if it is ideal op amp, here it should be 0, but if it's a non-ideal op amp, then there will be some voltages exiting here. So in order to make this voltage to 0, we are going to have a offset voltage. So that offset voltage will nullify the V minus value to 0. Okay. So now V minus nothing but the offset voltage, which is given as 1 millivolt. Okay. So therefore V naught we can write as 1 plus R divided by R1 into, instead of V minus we can write as offset voltage, VIO. Okay. So now we have the value of RF and R1. If we substitute the value, 1 plus 1 mega ohm divided by 1K into, actually the offset voltage, actually we have to consider the offset voltage as plus or minus 1 millivolt. Okay. If it is for inverting terminal means we have to consider plus millivolt, and if it is for if it is for inverting terminal, we have to consider as a plus offset voltage, and for non-inverting terminal, inverting terminal means we have to consider the offset value as negative, and for the non-inverting terminal, we have to consider the offset value as positive. Therefore, the offset voltage generally plus or minus. Okay. So actually, we have to write here as plus or minus 1 millivolt. Okay. So now we have to substitute all the values. We'll be getting 1 cancel. Here we having mega ohm. Here we having kilo ohm. Here we having millivolt. So therefore, finally, to simplify the equation, we'll be getting V naught is nearly equal to plus or minus 1 volt. So why it is plus or minus is actually the offset value may be either plus or minus. If it is plus, it is plus or minus. Okay, so we have to consider the offset voltage for both inverting and non-inverting terminal. Therefore, V naught is going to be plus or minus 1 volt. So the answer for the question is option C. And we move on to the next question. In figure, the operation amplifier are ideal and their output can swing between minus 15 and plus 15 volt. Sketch on same diagram the waveform of voltage V1 and V2 as a function of time. You must give the value of important parameter of the sketch. Okay. So this question and the fifth question both are similar type of question, but the only thing which is differ from is we have the separate. We have the circuit diagram is differ from fifth and seventh question. So the question pattern is same thing. So we have to draw the waveform. And first what we have to do is actually if you take a diagram, so we have two section. So this is the first section and this is second section. If you take a first section, we have the inverting terminal is grounded and non-inverting terminal is connected to the 3 kilo ohm and 1 kilo ohm resistance. So therefore the first part is nothing but it is a non-inverting amplifier. Okay, so here the input is applied to the positive terminal, therefore it is a non-inverting amplifier. And if you take a second part, it is nothing but it is a integrator. So we have the resistance here and we have the capacitance here. Okay, and one more thing is here we have the negative terminal is grounded. So therefore this part is also going to be act as a comparator. So if the value of positive terminal is greater than negative terminal, then the output of this first section is going to be plus V saturation. Similarly, if the output of the positive terminal is lesser than the negative terminal, means then the output of the V1 is going to be minus V saturation. Therefore, it will be operated as a comparator here. So now the output of the comparator is nothing but generally will be getting square wave. Okay. So now if the square wave is given to the integrator, then what will happen to the V2? That we have to find. Okay. So now we have to write the condition here. As I said, so if V1, so here it is given V1 value was ideal and the output can swing between minus 15 plus 15 volts, which on the same diagram. Okay, so the output value is between minus 15 to plus 15. So if V1, so if V1 is greater, okay, if the output of V1 is plus 15 volts, so when it will be plus 15 volt is if the positive terminal value is greater than the negative terminal. So if it is greater than negative terminal, then the output of V1 is going to be plus 15. So if the positive terminal is going to be negative lesser than the negative terminal, then it is going to be minus 15 volt. Therefore, V1 will be plus 15 plus or minus 15 volt. Okay. So now after writing V1 value, then we have to apply the KCL here. Okay, we have to apply the KCL at V plus. So if you apply the KCL V plus, you'll be getting we have the V1. So here we have V plus divided by 1K plus V plus. So V2 minus, that is V plus minus of V2 divided by 1K. Then here you will be getting as V plus minus of V1 divided by 3K. So if you simplify, you will be getting V plus is equal to 1 by 7 into Vi plus 3V2. Let it be equation 1. Okay. Now we got V plus. So we got V plus equation. And now we have to write what is the output of V2 here. So V2 is nothing but the output of the integrator here. So V2 is nothing but integration of minus 1 by RC integration of VA of t. So here VA of t is nothing but V1. So therefore V2 is nothing but minus 1 by RC integration of V1 into dt. Okay. So RC value is given. Therefore RC value is minus 1 by 3 into 10 power 3 into 0 to t V1 dt. So now let we have two conditions. One is V1 value will become plus 15 volt and V1 value become minus 15 volt. So for plus 15 volt means if the positive terminal value is greater than negative terminal, you will be getting V1 value is plus 15 volt. If the positive terminal value is lesser than the negative terminal, then it is going to be minus 15 volt. Therefore, we have to find for both plus 15 volt as well as for minus 15 volt. Okay. So now let me find what is happened for plus 15 volt. So V2 is nothing but minus 10 power 3 by 3 into, so V1 value is 15, so into dt. So you'll be getting minus 5 into 10 power 3 into t. So let it be t equal to 1 millisecond. This is t equal to 1 millisecond. For positive, for the positive value of plus 15 volt, let t equal to 1 millisecond. So if you substitute 1 in t millisecond, if you substitute the value of t here, you'll be getting a V2 which is equal to minus 5 volt. So now we got V2 value is minus 5 volt. Okay, and V plus is not important. If you know, we can also find V plus. So we already got V plus value as 1 divided by 7 into VA plus 3V2. So if you substitute the value here, we'll be getting V plus value as 0 volt. So now for V1 equal to minus 15 volt. So what will happen for minus 15 volt? So if you substitute the value, you'll be getting the value of V2 is equal to 5 into 10 power 3 into t after integration will be getting 5 10 power 3 into t. So now the duration, if it is plus 15 volt means we are considering time period as 1 millisecond. If it is minus 15 volt means we have to consider the same time period 1 milliseconds. So what will happen for the same 1 milliseconds of time? We'll be getting again you'll be getting the value of V2 value as, which is equal to, actually I have not mentioned here, you'll be getting V2 value as plus 5 volt. Okay, so 1 in 10 power minus 3. So here instead of t you have to write 1 millisecond. So 10 power 3 and 10 power minus 3 will be cancelled, therefore you'll be getting V2 value as 5 volt. Okay, so for plus 15 volt of input you'll be getting V2 value as minus 5 volt. For minus 15 volt of input you'll be getting the V2 value as plus 5 volts. So if you draw the diagram, we'll be getting, so this one, so this square wave is called as nothing but the waveform for the V1. So this is a V1. Okay, this is a V1. So V1 is nothing but it is a comparator. It will be working as a comparator. Okay, the output of the comparator is nothing but square wave, that is plus or minus V saturation. So if it is plus V saturation means, then what about V2? Okay, so if it is plus V, that is plus 15 volt means you'll be getting V2 value as, okay, what is happened for plus 15 volt? Actually for plus 15 volt you have the value of V2 as minus 4. So it will be actually here you have to draw from here. Okay, so minus 5 volt to, sorry, okay, so for V2 V1 is equal to plus 15 volt. So for plus 15 volt we'll be having the V2 value as minus 4. So actually I have wrongly drawn the diagram. So it will be start from here. Okay, so from minus 5 volt to, then it will be increases to up to plus 5 volt for the V1 value as minus 15 volt. Okay, for minus 15 volt you'll be getting the value of, sorry, it will be getting the value of the V2 as 5 volt. Okay, yeah, correct only, yeah, correct only. So for plus 15 volt the value of V2 should be start from here, and after it will be getting for minus 15 volt it will be to the plus 5 volt. So it's correct answer only. Okay, so this is the answer for the question, and let's move on to the next question. The circuit of given figure uses an ideal op-amp. For a small positive value of V in, the circuit works as a dash. I think if we can directly write the answer here. So instead of feedback resistance, here we have the diode as a feedback. Then what is the circuit? So here 4 options are given: half wave rectifier, a differentiator, a logarithmic amplifier, and exponential amplifier. Can you guess what is the answer? Actually, the answer for the question is it is a log amplifier. Actually, the answer for the question, it is a logarithmic log amplifier. So if you not know that, you can derive the answer. Okay. So now it is clearly given. It is an ideal op-amp. So ideal op-amp means here the voltage at this node and this node is going to be same. So here it is 0. So here it is 0 means here also it is going to be 0. Okay. So V plus and V minus both are going to be 0 here. Now we have to find what is V naught. Okay. So this is a condition. Actually, this is ideal characteristic condition. That is a infinite. The input impedance is infinite, and open loop gain is also infinite. Therefore, V naught is equal to A oil into VAD. Therefore, VAD is equal to V naught divided by infinity, which is equal to 0. So VAD is nothing but the difference voltage. Okay, the difference of voltage should be 0 if an op-amp is ideal. Okay. Now we have to write what is VAD here. So we know that V plus and V minus both are going to be equal. Okay, now what we have to do is we have to find what is the current flow through the diode. Okay, so we have to find what is the current flow through the diode. If you know what is the current flow through the diode, we can easily find what is V naught. Okay, so now we can write what is the current I. So what is the current I flow through here, through the non-inverting terminal. Okay, so I is nothing but, so here I is nothing but V in by R, and here we have to apply the formula of current flow through the diode. We know the current flow through the diode formula is I is equal to I naught into e power V by Vt minus 1. This is the formula we are going to apply here. Okay, so we can write I is equal to V in minus 0 divided by R, which is equal to V in by R. Let it be equation 1. Now we have to write what is the equation for current flow through the diode. It's nothing but I is equal to I naught into e power v by vt minus 1. So here e power v by vt minus of 1 is nearly equal to e power v divided by vt. So we can write as I is nearly equal to I naught into e power v by vt. Now we need what is v. Okay, so to find v, we have to take natural logarithm on both sides. Okay, so if we take natural logarithm on both sides, then exponential will be cancelled. Therefore, v is equal to vt into ln of I divided by I naught. Okay, so now already we got I equation as v divided by r. Therefore, we are going to substitute the value of I here. And what about for v? So v is nothing but here v is nothing but minus of v. Okay, so v out is nothing but minus of v. Therefore, we can write instead of v, we can write as minus v. Therefore, v is equal to minus v out is equal to vt ln of v in divided by I naught r. So instead of I, we can write as v in by r. So if you see the equation here, so vt is nothing but thermal voltage. This is constant, and the input voltage is also we have the I naught. So I naught is also going to be constant, and the resistance value is also going to be constant. Therefore, we can write output voltage is directly proportional to the natural logarithm of input voltage. Okay, so from this equation we can write output voltage is nothing but it is directly proportional to the natural logarithm of the input voltage. Therefore, the given circuit is nothing but it is a logarithmic amplifier. Okay, let's move on to the next question. Assuming that the op-amp amplifier in given figure is ideal, the current I through the 1 kilo ohm resistor is dash. Okay, so we have to find what is the current flow through this 1 kilo ohm resistance. So here we have the 2 milliamps of current just flowing through the inverting terminal, and feedback resistance is given, which is 2 kilo ohm, and at the output voltage we have one more resistance which is given as 2 kilo ohm, and we have to find what is the current flow through the 1 kilo ohm resistance. Okay, so it's very simple. So this is circuit diagram which is given. So here the current flow through is 2 milliamps. So if it is 2 milliamps means, so here the current flow is 0 according to ideal op-amp. I plus and I minus should be 0. So therefore towards, so into the inverting non-inverting the current is 0. But if you take a feedback through the feedback path, the current flow is again 2 milliamps. So here also the same 2 milliamps current will be flow through this feedback. So here the current flow is 0 according to ideal op-amp. The current flow through the inverting non-inverting is 0. So therefore the all current will be flow through the feedback path. Therefore the current flow here is 2 milliohm. So here it is 2k resistance is given. So 2k into 2 milliamps, it will become 4 volt. So V is equal to I into R. Okay, therefore the voltage at this resistance is going to be 4 volt, which is 2 into 2 k into milliamps, it will become 4 volt. Okay, so now here this is a current which is we have to find. So this is a current we have to find, and here one more resistance which is given, which is 2 kilo ohm. So actually the current flow through this junction is equal to through the voltage across this 2 kilo ohm resistance. Therefore here also it is going to be 2 milliamps. So here also 2 milliamps, here also 2 milliamps. Now we have to find what is for I here. So we have to apply KCL. So here it is towards here also towards junction. Therefore I plus 2 plus 2, which is equal to 0, you'll be getting I is equal to minus 4 milliamps. Okay. For the ideal op-amp circuit of figure, determine the output voltage V0. Okay. So we have to find what is V0. So here they have given the circuit, and we have to find what is V0. Okay. So first to find V0, we have to what happened for this node and this node. So first we have to find what is the voltage at here, and what is the voltage at here. So if you know these two voltage, we can find V0. So first we have to apply we have to apply the KCL at the inverting at this terminal. Okay, so first we have to apply V plus. So what is happen? What is the equation for the V plus? So if you apply the KCL here, so we have two resistance here. So this is 199 ohm resistance. Here also we have 100 ohm resistance. So here we have to apply the nodal voltage. So KCL is equal to what will happen, that is VI. So V plus uh, V plus minus. So if you apply the KCL, you'll be getting V plus for this one. So V plus minus 4 divided by 100 plus V plus minus V naught by 99. So this is one equation. So if you simplify it, you'll be getting V plus is equal to V naught divided by 99 plus 4 divided by 100. Similarly, we have to apply for the next terminal. So if you apply for the next terminal, you'll be getting V minus of minus 4 divided by 100 plus V minus of minus 0 divided by 100. So from this equation, we got V minus. So for this one, okay. So first we applied the nodal for this V plus. So if you apply V plus, you'll be getting the simplified equation as 199 V plus equal to 100 V naught plus 396. This is equation 1. And if you apply the KCL at this nodal point, you'll be getting one more equation. So which is nothing but V minus minus 4 divided by 100 plus V minus minus 0 divided by 100, which is equal to 0. So if you simplify, you'll be getting V minus is equal to plus 2 volt. Okay, we got V minus as 2 volt. So here the circuit is an ideal op-amp. Ideal op-amp means V plus and V minus both are going to be same value. So now we got V minus value as plus 2 volt. Therefore, V plus volt is also going to be same. That is V plus volt is going to be the minus 2 volt. Okay. So if it is plus 2 volt means then V plus is going to be minus 2 volt. So if you substitute the value, you'll be getting if you substitute the value of V plus in this equation, you'll be getting the V naught value. So V naught value was 20 millivolt. Okay. Let's see the last question. Find the output voltage V naught in the following circuit, assuming that op-amp are ideal. So we have to find what is V naught. So to find V naught, first we have to find what is happened to the voltage here. So here op-amp is an ideal op-amp. Therefore, here it is 1 volt means here also it is going to be 1 volt. Okay. So here it is also going to be 1 volt. And first we have to find what is the output of the first section. So we have to find what is the output V naught of one of the first op-amp. So if you know what is the output of the first op-amp, then we can easily find what is V naught. Okay. So here it is 2 volt and here also it is going to be 2 volt. So due to ideal op-amp, the voltage at this node and this node both are going to be same. Therefore, here also it is going to be 2 volt. So here it is 2 volt means here also it is going to be 2 volt. So now we have to apply the nodal voltage here. So by applying nodal voltage here, we can find V naught of 1. So apply KCL at 1 volt. So we have to apply the KCL here at 1 volt. So by applying that, we are getting equation as 1 by 2 plus that is 1 by 2 plus 1 minus 1 minus V naught of 1 divided by 2, then 1 minus 2 divided by 1. So 1 minus the voltage here is 2, 1 minus 2 divided by 1, which is equal to 0. So if you simplify, we'll be getting V naught of 1 value as 0 volt. So now we got V naught of 1 value as 0 volt. And now we have to apply KCL at here. So if you apply KCL at here, then we can easily find V naught here. So if you apply KCL at this 2 volt, you'll be getting 2 minus 1. Okay, so 2 that is 2 2 minus 1. So here what is 1? So 2 minus 1 by 1 plus 2 minus V naught divided by 2. So then 2 minus V naught divided by 2. So 3 junctions are there. So here one term, here one term, and here one term. So if you simplify, you will be getting V naught. So V naught 1 value is already known, which is 0 volt. So you have to substitute the V naught 1 value here. So the remaining term is V naught. So V naught is we are getting value as 6 volt. So the answer for the question is 6 volt. Okay. So thank you for all the participants. So we have come to the end of the module 5.